the first Mathsheetz has just dropped on mathsheets.com. Link in the description. So this Mathsheetz is completely free. It's posted online. You can download it for free. It's on complex analysis. There's the difficulty level is kind of upper level undergraduate to introductory graduate. I know it says graduate here, but of course it's because I made it for a graduate course at the University of Utah. But I think it could definitely apply to any undergraduate course. It might go a little bit more into some things you wouldn't cover in a traditional undergrad course, but that's probably a good thing to study anyways. So yeah, if y'all would just download this and kind of check it out. It's 30 pages of basic, kind of starts with the very basics of complex analysis. I assume that you are familiar with some level of, complex variables. So I kind of put a first page as like a preliminary background deal, but then it basically assumes that you already know all this stuff. And it kind of jumps right into all the crucial theorems that you need. It's very compact. It's putting several chapters of multiple textbooks into very condensed form, and so we have like all the crucial theorems that are just like thrown at you and immediately proved, um, pretty much all the way up into the Riemann mapping theorem. Everything important that you might need. Uh, Obviously there might be a few theorems missing here and there, but pretty much all the crucial theorems that most complex analysis courses go through, culminating in the Riemann mapping theorem, are like covered with their proofs explained, and the proofs are pretty much directly from textbooks, um, with slight modifications that I've made, but most of these proofs are coming almost entirely from the structure of Donald Marshall complex analysis, as well as Stein and Chikarsky complex analysis. So yeah, I put a lot of work into this. I used it personally to study for my complex analysis exam, which I took at the graduate level, and I found it extremely helpful, not only to write this, but to kind of read through it, and it helped me review the concepts and the material that we had covered over, so many lectures, the course of a whole semester. Now, I will say that, you know, before I get to the Riemann mapping theorem, there's a little bit of, or good amount of stuff on Mobius transformations. That's because our class covered these pretty heavily, and turns out they're really important. So it's pretty cool stuff. This isn't something you'd see in an undergraduate level course, but it's really good stuff to learn, and it pretty much goes over Mobius transformations from the very start, explains what they are, linear fractional transformations, and like why they're useful. So that's something that this this Mathsheetz kind of really focuses on, and then gets a little bit and tiny bit touches on hyperbolic geometry and the uses of that. But you might want to consult, like, for a more rigorous treatment. It's kind of like a page on hyperbolic geometry. You might want to consult a textbook and have some background. This is if you wanted to get into kind of this stuff on hyperbolic geometry. If you've seen it before, then it's a nice little review, a few paragraph review of some concepts of how you would like form a hyperbolic geometry on the unit disk. And then we get into normal families, and all the machinery is developed. And then finally, the Mathsheetz culminates in the proof of the Riemann mapping theorem. As you can see here, it's about 1.5 pages long, and I have a little sketch of the diagram of like what's going on in the proof, because there's kind of a lot that goes into this proof, and it's very important. It basically states that, for those of you who don't know, it states that if you have any simply connected open set in C, then there's a biholomorphism between that simply connected open set and the unit disk. And of course, sorry about that. Somebody was at the door. So we basically have a simply open connected set, and there exists a simply connected open set. There exists a biholomorphism between that and the unit disk. Okay, so that's the statement of the Riemann mapping theorem. It doesn't provide an explicit biholomorphic map because sometimes they can be extremely analytically difficult to find, if not impossible. However, just knowing the existence is kind of a big deal. It has a lot of implications in, for example, partial differential equations, because if I give you some weird disk like this guy, this pear-shaped disk, then, and say you know something about the boundary of the disk, you're heating the boundary, and you want to know how heat is going to spread along the region, well, you can, if you know, or at least can numerically approximate a Riemann map, then you can Riemann map it to the unit disk, solve the heat equation on the unit disk using those boundary conditions, and then inverse map back to the weird set that you started with, and that gives you solution to a differential equation with like very weird boundaries. So this stuff is super powerful, especially for numerical solutions of PDEs in the complex plane or in two dimensions. And if we scroll down further, after I give the proof of the Riemann mapping theorem, I kind of go into more advanced theorems and don't really go deep into their proofs. That's something maybe I can expand on later. I just kind of didn't really have the time, and also necessarily the best background to really go in depth on these theorems. So I encourage you to check them out, and then maybe if you're looking for the proofs, you would have to reference other sources, or possibly look at the textbooks that I use to write this Mathsheetz. So yeah, for the more advanced theorems, I kind of just state them explicitly, and notice this Schwarz-Christoffel theorem or integral basically tells you how to explicitly construct a Riemann map from a polygon into the unit disk. And this is extremely useful because, numerically, if you give me some weird simply connected open set, I can approximate it with, a polynomial of arbitrarily many vertices, and using that approximation, I can, obtain an approximate Riemann map between any given open set and the unit disk. So that's one way that an explicit map can be constructed, at least a numerical approximation of one. And then we get into the Mittag-Leffler theorem, which is constructing functions, meromorphic functions with prescribed singular parts and no other singular parts in omega, which is also very important. um, Weierstrass P functions, kind of some of the more advanced functional theory um, is kind of touched upon after I kind of prove the Riemann mapping theorem, and I don't go deep into this stuff. I just finish it off with this 2-line uniformization theorem, which of course is extremely important to the field of complex analysis. It's almost a generalization of the Riemann mapping theorem. um, but I didn't really go in details onto how to prove this thing, and there would be a lot of machinery required, and would have to be developed to attempt to prove this. It'd probably take another 10 or so pages. In my, I would expect probably 5 to 10 pages more of just theory and machinery to even prove the uniformization theorem. So I went ahead and left the proof out of this edition of the Mathsheetz. I may, at a later time go back and revise and add more. But for right now, I think this is more than enough coverage for almost any undergraduate class, and probably really useful for even the graduate level. So hopefully y'all will take the time and check this out and read through it. And if there are any problems, any mistakes, if you could please, leave a message in the comments, um, or send me a message via the website mathsheets.com. That would be much appreciated. Anyways, hope you all have a nice day.